So one of the requirements for time series analysis is that the time step has to be uniform across the dataset. Well, what's a time step, you ask? Time step is the difference between two consecutive data points as far as time is concerned. So in our example, since our data is on a monthly cadence, each time step is a month. So first, before checking what data is missing or problematic in our time series data, we need to have a final expected date range, which we can programmatically generate using the date underscore range function present in the pandas library. There are three common problems that we find in a datetime index. One is missing date, second is unexpected date, and the third is duplicate date. We will explore more of these problems in the next slide. Once we have programmatically generated our final date range, it's quite straightforward to check for each of the three common problems that you would find in our datetime index. For example, missing dates are those dates that are absent in our index but are present in the final expected range. Unexpected dates are those dates that should never have been there to begin with, which means they are absent in the expected final range but are present somehow in our index. And duplicates are even more straightforward. They are non-unique entries of dates in our datetime index. What if our dataset had null entries? Well, fortunately, our passenger dataset does not have any, but what if our dataset had? We can make use of the fact that the time series has a nice chronological order built into it to make some smart imputation choices. For example, consider this modified version of the passenger dataset that we built to demonstrate the same. We artificially encoded certain NaN values throughout the dataset and see how we can impute them. So we make use of the interpolate method, right, which works by looking and comparing values before a particular null value and after the null value, which are non-null, to smartly impute the specific null value in question. You can compare the two columns, passengers missing and passengers imputed, to see the difference. There are 5 distinct characteristics or properties of a time series that you need to care about. The first is trend. A time series with a positive trend will see its average value increase with time, and a time series with a negative trend will similarly see its average value decrease with time. Second is seasonality, whether patterns occur regularly over time. Third is outliers, and we have seen this before in pandas, numpy, and the initial machine learning topics. These are drastically different values. The fourth is impact, also called holiday effects, whether specific points in time have very sharp changes in value associated with them. And the last but not the least is stationary, which is a very important property, which requires the rolling mean, frequency, and amplitude of the time series to be consistent across time. Now, these 5 properties are quite important because they help you understand your time series better. There are certain statistical models like ARIMA, which requires your time series to be a certain way. For instance, they need to be stationary for ARIMA to be applied onto the time series. And lastly, for structured time series models like Profit, which we'll be covering later on in the module, we need to explicitly specify some of these properties when we define the model. Okay, let's relate what we just learned with the passengers dataset that we are working on. Does the dataset have a trend? Yes. As we move from left to right in this particular graph, we can see that the average value of passengers seem to be increasing with time. So there is a positive trend in our particular time series. Second is seasonality. So there seem to be regular ups and downs with a roughly monthly pattern in the particular time series that we are working on. Third is outliers. No, there are no sudden or drastically different values as far as visual inspection reveals to us. Fourth is impact. The curve is reasonably smooth, which means that there are no sudden upticks or downticks, so no holiday effects as well. Fifth is stationary. So the time series is not stationary because although the frequency remains more or less steady throughout the duration of the dataset, both the rolling mean and the amplitude is increasing. All these properties can be obtained visually by using Seaborn to construct a line plot of our time series. The raw values of most of the time series that we work with are pretty chaotic in nature. Consider the problem of stock price prediction, which is a smooth curve over larger time horizons, but very jagged and and seemingly discontinuous at very low resolutions, like on a daily level. So window functions are exceptionally good to smoothen out such kinds of data, such that general trends and seasonality are immediately revealed to the user. And there are other benefits of using window functions that are mentioned in this particular slide. So there are two kinds of window functions, expanding and rolling, but we will focus only on rolling for the time being. And the rolling function is invoked using the rolling method, which is present for both Panda series and data frames. And that can also be used to check whether a time series is stationary or not. Broadly speaking, it asks the question, what's the mean of the past n values at this point in time? So this is the example of a rolling mean. There are similar formulations for rolling standard deviation, etc., which we will see in later slides. Remember how we said that the passengers data set is not a stationary time series because both the rolling mean and the amplitude varies with time? Well, let's try to arrive at the same conclusion, but not through visual inspection, but through rolling statistics. We build a rolling window, which is 12 months apart, and we plot three things in this graph. The original data set is plotted in red, the rolling mean is plotted in blue, and the rolling standard deviation is plotted in purple. What does the graph say? So as you can see, the rolling mean seems to be steadily increasing with time. That's one reason why the time series is not stationary. What about amplitude? As you can see, rolling standard deviation is a standard for amplitude, the variation of the particular value of the time series in that window. And that too seems to be unsteady as we move from 1950 to 1960. Yet another reason why the time series is not stationary. Sometimes we are not interested in the specific value of the data set, but we are more interested in whether the data increased or decreased compared to the last time step. This is called differenced data. And when you plot differences in a histogram, we get what is called a histogram of differences. So the difference data is obtained by simply invoking the diff method on the data frame or the relevant series in question. Since we are doing difference between time steps, the diff method often results in rate of change of the particular column that we are interested in exploring. So for instance, if you're looking at stock price prediction, then the difference data set will give you an idea of how often the stock went up or down. Okay, let's see how a histogram of difference of our data set looks like. So on the left subplot, you have the raw values plotted to give you an indication of how the data set looks like. And on the right subplot, we plot the difference data. Interestingly, most of the differences follow a normal distribution with most month-to-month changes centered at zero and then having a reasonably equal left tail and right tail. However, there are dips. So for instance, consider the outlier of minus 100, which means that in a particular month-to-month change, the number of passengers dropped by 100 units. So that's the kind of insight that you can obtain visually from inspecting the histogram of differences. Lag is a very important idea in time series. Simply put, it's the time difference between two time series samples or rows. For example, like if a lag of 5 is basically the difference between time series samples that are 5 rows apart. So a lag feature is when we bring the value of a time series, k steps in the past away from the present, as a lag feature into the present. This is a very useful predictor when we look at traditional machine learning techniques later on in the module. Let's look at our data set. So each successive time step in our data set is a month, right? So we can assume that the data points that are 12 months apart might be correlated with one another. So we can introduce a lag of 12, which means samples that are 12 months apart are brought to the particular present as features. And there is an assumption of temporal ordering in time series, and that kind of dictates how much lag that you want to introduce into the time series to generate such features. These can be easily generated using the shift method of pandas, which is available for both data frames as well as series. So, how far back into the past should we look at? It depends on the problem. For instance, in this slide, we kind of outline an analysis that we do for investigating whether there is a monthly correlation. We can do so on a quarterly basis, yearly basis, half yearly basis, daily basis, weekly basis, etc. Needless to say, it's quite inconvenient to try to do this analysis for every possible cadence that we could think of. That's why there is a nifty automated way to quickly arrive at different lag features that you would definitely want to include in your data set thanks to the stats model package. There are two functions that we can make use of. One is the autocorrelation function or ACF, and the second is the partial autocorrelation function, which is PACF. We will see more of these functions in the next two slides. Autocorrelation is a measure of how well a particular dependent variable is correlated with itself, with specifically values from the past, right? And autocorrelation functions can be easily plotted in a way where y-axis is the strength of correlation varying from -1 to +1, and on the x-axis you have different lag values. So if you look at the graph below, which is the autocorrelation function plotted for the passengers data set, you can see that the value is 1 for a lag of 0, which makes sense, right? Because the time series is correlated with itself. And as we move from left to right for different lag values, we can see the correlation increase or decrease. Of special note is the shaded region, which represents the uncertainty range. For a reading to be meaningful, it has to be lying beyond the shaded range. So for instance, all values after lag of 15 are present inside the shaded region and hence can be neglected. Partial autocorrelation function is exactly like autocorrelation function, except that it eliminates all the dependencies from intermediate type steps when the plot is being generated. For instance, the specific question that it answers is how much does the value from 2 days ago explain today's value, which cannot be explained by yesterday's. The function can be plotted using plot underscore PACF, which is present in the stats model package. As we saw earlier, seasonal patterns are patterns that repeat regularly over time at different cadences, like monthly level, quarterly level, etc. The specific cadence of repetition really depends on your data set and the problem at hand. So, stats model has a very nifty seasonal underscore decompose class that uses very simple additive and multiplicative time series models to tease apart the different components of your time series into trend, seasonal, and residual. Residual is nothing but whatever the value of a time series is that cannot be explained by the trend and seasonality. So, the seasonal underscore decompose class returns an object which has a ton of attributes that lets you access each of the individual values directly, like trend, like seasonality, and also has a nifty plot method that lets you plot all the different components in a nice subplot grid, as we can see below.